So hi everyone, and thank you for introductions. So I'm happy to be here to present our work. This is practical multi-party private set intersection from symmetric key technique. And different from two previous presentations, our work focus on multi-party settings. So our protocol is the first protocol from symmetric key techniques. So it's quite efficient. So it is a joy to work with Vlad, Nao, Benny, and Mike. So let's start with a simple scenario. Here we have three parties, Alice, Bob, and Charlie. Each party has a set of items, and now they want to compute the intersection of their set on the way that don't leak any information except for the intersections. So different from two-party PSI, they have several secure requirements for multi-party setting. The first one is the party learns only the intersections and nothing about the partial intersections. And the second thing is if the parties corrupt, so for example here Alice and Bob corrupt, they can exchange the message, but they do not allow to learn anything about the Charlie's dataset beyond the intersection items. So PSI have many applications that you've seen before. And my favorite one is decentralized social networks. So in this scenario, we have some Facebook users, and they have a list of friends. And now they want to see the common friends of them. So they can run multi-party PSI. Yeah. And unlike two-party PSI, they have very few works focusing on multi-party settings. And all of them based on oblivious polynomial evaluations. And it's implemented using additively homomorphic encryptions. And because if the set size is large, so it is quite inefficient. So it's heavy on public keys operations, and this requires homomorphic encryptions for each items. So our protocol is from symmetric keys operations, so it's scalable for the larger sets. For the rest of my talk, I will present our PSI approach. And we first introduce a new tool, which we call oblivious programmable PF. And then we will show our zero sharing protocol. And next step is we will present how to put it together to get our PSI constructions. And this talk is on semiotic settings when the party just follow the protocol. So before going to our oblivious programmable PF, I would like to revise oblivious PF functionality. So in OPF, Alice inputs X into the functionality and receives f of X. And Bob receives the key. So last year, we proposed a weaker version of PF where the key is related. And it is efficient. It requires only 5 microseconds in amortized setting. And OPF were used to construct two-party PSI. So now what the oblivious programmable PF means? It means that Bob can program the output of PF. So for example, here Bob has some specific points, and Alice has the query X. So if X equals some Xi, Alice gets Yi. Otherwise, Alice gets a random value. And for the security purpose, our protocol requires that all of Yi's are randomly distributed. So now I'm going to present a simplest protocol, which is called polynomial-based OPF. So it has the best communications. So we can think that at least Bob has some points and it's put in the graph. And now if Alice have the S1, Alice see Y1. And if Alice have X primes, which is doesn't equal to any Si, she get the random values. So this is the functionality of our OPF. So our polynomial OPF construct as follows. We first run oblivious PF. Alice have input X and receive f of X. And both receive a key. Now because Bob have the keys, he can compute any f of xi. And then he builds a polynomial p of x on the points si and yi XOR to f of xi. So you can see a green point here. This is S1 and y1 XOR to f of S1. So now Bob sends the polynomial to Alex, and Alex output p of x XOR to f of x. For the correctness, if x equal to xi, for example here S1, so Bob Alice know f of x, so which is equal to f of xy S1, and this means the line green line null by Alice, so she can output yi. So look at another point. Here is x primes, and a green line here. Alice doesn't know because the functionality of OPF. Therefore, she outputs random values. So for the security purpose, perspective, for pseudo-randomness, hide everything about the value of f for h which not equal to si. So I'm going to evaluate to say about the cost of our polynomial OPF. So for communication, we need ON square, and for communication, we need ON. And we also split number of point n here into small n, so n around 3 by using hashing technique that you hear before. So we also have two other OPF protocols that have the trade-off between number of computations, number of points, and number of queries. And we have a protocol that's linear in communication and computations. So this one can be seen in the papers. So we are done with our OPF constructions. Now we move to our zero sharing protocols. And the purpose of zero sharing is that if all the parties house the same items, here is X, the party will house the correct zero sharings. So it means that the XOR of the shares equals to 0. And now if some of party PIs house the different items, X primes, so here for example, P1 have X primes. So P1 will house incorrect zero sharings. So it means the XOR of the shares doesn't equal to 0. So I'm going to present one of our zero sharing protocols. This is a non-interactive zero sharings. And we have the interactive versions, which is you can see in the paper. So the first step is the party choose the random keys and send to other parties. So for example, here P0 choose 3 keys and send to P1, P2, and P3. And now P1 choose only 2 keys and send to other party. So on and so far. So each party have 3 keys. And now if X is the intersections, the party compute f of X under the keys and then XOR them to get the zero sharing. So P1 do the same thing. So now looking at the XOR of the shares, you can see that the f of x under the key 0, 1 appear in P0 and in P1. So it will be cancelled out. And another example here is f of x under the key 0, 2 appear in P0 and P2. Yeah, so it will be cancelled out. So on so far. So then it means that the XOR of the share equal to 0. And if x isn't in intersections, so for example here P1 have x primes, P1 compute the share of f primes, which is equal to that one. And now we again look at the XOR of the shares. We can see that the f of x primes under the key 0, 1 appear only one time, and f of x and this one f of x prime doesn't equal to any f of x. Therefore, the XOR of them doesn't equal to 0. Yeah. So the important things in non-interactive zero sharing is that we can send in the keys in one-time event, and you can have unlimited number of zero sharings. Yep. So we are done with zero sharing protocol, and we have our tool is the oblivious programmable PF, and now we will show how to put it together. So we can consider a simple case. This is when the PSI of one item only. And the idea is if the party have the same x, the XOR of them will equal to 0, and otherwise it is random. So it's either our zero sharing protocol. And now the question is who can check the XOR of the shares? So we choose one party be a leader, and then now another question is how to send a share. So we can send it directly, but however it's insecure because the subset of correct parties can compute the correct share of honest parties, and the share can leak the honest party items to adversary. So we use our new tool. This is OPPF. So a leader receives a correct share if he have the common items with the sender. Otherwise, he learns nothing. So in this scenario, first we have the zero sharings, so that each party, and if X is the intersection items, so each party will receive a share, and the XOR of the shares is equal to 0. And now we choose P0 as be a leader, and then the party create a point X and the share of X. So, and now P0 and PI involve OPPF. So we have here we have the leader query on X, and the leader will receive the correct share of P1 because the leader have X and the same as P1 have. So similarly, the leader receive correct share of P2 and correct share of P3. And now because the X is the intersections, so the XOR of them equal to 0. So the leader can check whether the XOR of them whether it's equal to 0. So if yes, so this is the intersection items. And now if X isn't in intersections, so we can say P1 have X primes, and from our zero sharing protocol, the XOR of them doesn't equal to 0. And now P0 and P1 involve OPF because a leader have X, but P1 have X primes, so they have different points. So the leader receive a random value. Therefore, the XOR of them doesn't equal to 0. So X is not in the intersections. So for the security, we guess almost our protocol is almost secure against semi-honest. Because if n-1 corrupt parties can interactively compute the share of honest parties. So here we have P0, P1, and P2 corrupt. They have all the keys. They can interactively compute the correct share of honest parties, here P2. And in our protocol, we have OPPF between P0 and P2. So because a leader have X and P2 have X, so a leader receives a correct share of P2. Now a leader can compare two shares and learn whether P2 have X. And important thing here is P1 have X primes. So X now is the partial intersections. So that they doesn't allow to learn here. However, this one leads no more than when all the corrupt parties have the same inputs as a leader. So this one calls secure in augmented semi-honest model. So to get the standard semi-honest model, we propose an interactive zero-sharing protocol. This one you can see in the paper. So now I'm going to talk about our implementation and evaluations. So we implement our protocol, and we are the first protocol from symmetric keys operations with constant rows. And here is the number of parties, and this one is the total running time in seconds. So if each party have 2 power of 30 items, and the length of items is 128 bits, our protocol takes 25 seconds for 3 parties, and we have our protocol is linear in the number of parties. So compared to previous works, for the computations, we require much less number of exponentiations, which is here, n of n kappa. And here n is much smaller than the number of set size. And this one is for this cost is for base OT, so it can be on the offline. And for the communications, our protocol is from symmetric keys operation, so we require more communication than protocol based on public keys operations. Yeah, and thank you.
So I'm just wondering, did the parties have to reveal the sizes of their sets to each other?
Yeah. Yes, I think all of the protocols for all 3 presentations, we review the set size. However, it can be fixed by set up the upper bound of the set size. Yeah, if you want to hide the set size.
Hi there, Vince from Alibaba, and great work. Can this protocol be run in the 2-party too? Can this protocol be run in the 2-party setting?
Yes, so it can run in. We have the we proposed a protocol last year, and this is run on two-party PSI. And this year we extend this one by to support multi-party PSI.
When it comes to the two-party setting, how does it perform?
Yeah, I can show you. Zero sharing. So here, this is the programmable PF, and when you set YI, EHI, so you can, yes, so when you set YI, EHI, so if you have the same items, you receive the same. You receive X, and if you don't have the same items, you receive random, and you don't know both items that is not in your set.
Okay, thank you.
Yeah, thank you.
So you mentioned that the communication cost for each user in this protocol is linear in its set size.
Yes.
So is that true for both the interactive zero sharing and non-interactive?
No, in non-interactive zero sharing, so you can think that each client interactive with a leader. So the communication is OM. Here M is the set size. But in our interactive, each client have to interactive with other clients. So N minus 2 clients. So we require all N time M. And here N is the set size and M is the number of parties.
Okay, thanks.
Yeah, thank you. Yes. Thank you. So we are trying to. Thanks for the question, but we try to improve our protocol, and so you can see the Facebook like the kind of decentralized social network. This is the social network is like they have many information, personal data. So we try to improve our protocol, and they have many variants of PSI, multi-party PSI, like threshold PSI. Yeah, so this is our future work. Yeah, I know this. Yeah. Oh, I see. Oh, yeah. 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 Okay, yeah, thank you. Yes. Yeah. Yes. Yeah, thanks.
Thank you, great work. I have just one question. So if I understood correctly, at the end, only the leader gets to know the result?
Yes. So in our protocol, the leader also the person who receive the intersection items, but you can have one more round sending to another client.
Oh, so the assumption is that if like multiple parties want to know the answer, the leader would send the answer.
Yeah.
I guess that would fit in the semi-minus security.
Can you?
Yeah. Thank you.
Yeah.